It's a cool spot. Yeah, please, your power bank.
Okay, Max. Yes, the following school student.
Good.
Okay, no, I'm charging my smartphone.
Good morning, ma'am. Good morning. Welcome.
Okay, Dr. Dumozu, can I share my screen?
I'm doing something.
I want to share my screen. Okay. Yeah. Good morning, everyone.
Good morning, sir.
Yeah.
Good afternoon, sir.
This is our physics pages 101.
Okay.
And I want to welcome you to this class. I will mute ourselves. Good morning. So that any of our is there. So
Whoa. He has been locked down. Please, sir, don't plead.
Can you leave point?
Hmm?
Can you leave point?
Sorry, I just mute my mic.
Just end the class and let's join again.
Can everybody hear me now?
Yes, sir.
Okay, good.
Yes, we can hear you.
I lost my connection here. Please, can we mute ourselves? At least for now we can.
Okay, sir.
Let's mute ourselves. So, like I was saying, we want to discuss about moment of inertia and see how far we can go today, and talk about one or two points under laws, Newton's law, actually the one that has to do with the rotation of the earth that is important to us at this point. We have done a lot of work in the area of mechanics, and mechanics is not complete without mentioning moment of inertia. Now, what is moment of inertia? And how do we quantify moment of inertia? How do the unit of moment of inertia? Then I ask you to mute your phone, to mute yourself. I ask you to mute yourself. A lot of noise background, they are disturbing us. Please do so. Now, we want to know how to calculate moment of inertia. Then that will take us to an important aspect on that moment of inertia, which is radius of gyration. And you have it on your screen there that I'm sharing with you. So when we want to discuss moment of inertia, for us to really appreciate this, you will talk about, we want to assume that we have a body that is divided into small particles. And when it is divided into small particles, you can say that, okay, this particle is mass 1, another one is mass 2, another one is mass 3, and so on and so forth. So you have a body divided into small particles, and you assign mass 1, 2, 3 to them. If you have 10 particles, if you are divided into 10 particles, then you have mass 1 to mass 10 of each of the particles. Then, of course, you now have, each of those particles will now have a distance to a fixed point. Let's call that point O. We call that point O. Then each of that particle that you have divided the body into, M1, we have a distance R1 to O. M2, we have a distance R2 to O. M3, we have a distance R3 to O, and so on and so forth until you get to as many as the number of particles that you have. So you assign the distance to the corresponding mass. You assign the distance to the corresponding mass, then you can now define the moment of inertia of that body about O, about the center, about the fixed point that you are talking about. So the moment of inertia is defined as M1 R1 squared plus M2 R2 squared plus M3 R3 squared, and so on and so forth to get to M, like if you have 10 particles, you have M10 R10 squared. That is the definition of moment of inertia. So if you have a system and you know the distance, you know the distance from a fixed point, then easily you can get your moment of inertia by multiplying the mass with the square of the distance and sum all the masses and the square of the distance together, and that gives you the moment of inertia. Now, the unit of moment of inertia is kilogram meter squared. Is kilogram meter squared. Of course, you should know that because mass in SI unit, mass is in kilogram, then R is in meter, but then you now square it becomes meter squared. So the unit of moment of inertia is kilogram meter squared. You see, in physics, it is very important that you are used with SI units of measurement. The unit is very, very important in physics. It is a very great thing. It is a sacrilege for you to work when your units are not consistent. You must be consistent with your unit. As much as it depends on you, always work in SI units. Always work in SI units. You know the SI unit of mass is kilogram. You know the SI unit of length or distance or radius is in meters, and so on and so forth. You cannot be working under this environment and you use kilogram multiplied by centimeter. That is a very great error, and it will cost you a lot of marks. So always know the unit of what you are talking about. We have defined moment of inertia. You have seen how to calculate moment of inertia. You have seen the unit of moment of inertia. So when you see questions on moment of inertia, you should be able to relate with that. Now, another thing that is closely related to moment of inertia is radius of gyration. It is radius of gyration, and we denote that as K. So there is a relationship that exists between radius of gyration and moment of inertia. And we are going to try and establish the relationship from definition. Then you can see how they relate together. So, what is radius of gyration? How do we relate it to moment of inertia? Now, moment of inertia of a body can be simply written as mk squared. You can see we have radius of gyration. You have radius of gyration. Radius of gyration. We have radius of gyration. You have R. Radius is also R. But now under this environment, we now replace that R with K, and having defined K as our radius of gyration. You know, when you were defining in moment of inertia, you have mr1 squared. Now, if you now say that R is a radius, and you are now talking about radius of a particular moment of inertia, then you can now replace that your R with K, which is also radius. That is why you have mk squared, simply written as moment of inertia. So moment of inertia, it can be written as mk squared, where K is the radius of gyration. This Abisola Fashino, you are disturbing us. I ask you to mute yourself. Now, we haven't said that. We said the moment of inertia of a body can be written as mk squared, and I've just explained to you that K is standing for radius, and we have defined a moment of inertia using radius before. So K is distance from the axis of rotation. K is the axis of rotation.
Sir, please, I cannot hear you. Yeah.
You cannot do what?
I cannot hear you. The other people that are not muting their mics. So,
sorry, can paramedicals join?
What are you saying? Come again.
Sir, it's
I couldn't hear you. Your voice was breaking.
The voice is breaking.
Yes, sir.
But you can hear me now. I said the voice is breaking. You said yes, sir. That means you can hear me clearly.
But like when you were talking before, the voice was breaking.
Okay. What is going to happen? You know, I cannot control the network. I'm trying to be as much as possible to get a stable network here.
Yes, sir.
So
So I think
what you can do is to follow what you have on the screen. Is that okay?
Excuse me, sir.
Yes.
So there's some people on the call that are not muting their mics, which is clashing with whatever you are saying. There are some people on the call that are not muting their mics, and it's clashing with whatever you are
Yes,
saying, sir.
I'll be announcing that now. I've asked everybody to move themselves, and they refuse to do so.
Sir, you can mute everybody.
Let me see.
Sir, you'll be checking the network, sir.
Yeah, I'm trying to mute everybody now. Okay. Okay, I think I've done that. So now just try and follow what you have on the screen. So I'm going to recap again so that at least since I've muted everybody now, so that we can all hear me very well. So we have defined moment of inertia. We have said it is M1 R1 squared. We have seen how the body could be divided and how we now relate it to distance and how we can now add it together. And I've also said that you can as well take note of the unit of moment of inertia as kilogram meter squared, and you can easily see how it is meter squared from R squared. Then this energy, I think I muted everybody now.
So my own question is this class?
Is this what?
Class also for pre-medicals?
If pre-medicals are doing physics 101, this class is for you. Okay, I don't know what physics you are doing, but if physics 101 is in your course that you have registered, this is physics 101. Oh, it's an aspect of physics 101, please. So we have spoken about moment of inertia. We have defined moment of inertia. We have I've told you the unit of it. Then we are trying to get the relation between the radius of gyration and moment of inertia. So we can see that we have replaced the R with the radius of gyration. Then we want to define what is radius of gyration. So wherever you see R, you can now put K squared. That stands for radius of gyration. Then what is K, which is radius of gyration? Radius of gyration is the distance from the axis of rotation to a point at which the total mass is seen to be concentrated.
Excuse me, sir.
Yes.
Please, they can't hear you on YouTube. They can't hear you on YouTube, sir.
Then what do I do? What do I do? You can hear me here now.
Yes, sir, we can hear you here.
Oh.
Just hear me here and get this material. The YouTube, I don't know. I don't have the setting of the YouTube here, so I suppose you should be able to hear me there. So listen to me where you can hear me.
Sir, I just checked the YouTube now. It's talking now. I can hear your voice on YouTube.
You can hear my voice on YouTube?
Yes, sir.
You people are distracting this class, so you have the screen. You better open your eyes and open your ears. I don't want any form of until I ask you any question. Don't interrupt me again. Until I ask you any question, nobody should interrupt me again.
Man, you fucking crazy, bro.
So we have moment of inertia. We have related it to radius of gyration, where you have K replacing R. We have K replacing R. Therefore, moment of inertia can be written as M K squared. as mk squared. Then we have defined radius of gyration to be k, and it is distance from the axis of rotation to a point at which the total mass is seen to be concentrated. Therefore, we can now make k the subject of formula to get the relationship between radius of gyration and moment of inertia. And if you make k the subject of formula there, you have k equal to square root of I all over n, where I, capital I, is the moment of inertia, then m is the mass. So you have an expression for radius of gyration there. Radius of gyration is what I circled on your screen. Radius of gyration is k, which is equal to square root of I all over n. This is very important because you will have to use it a lot. So we have different symmetry. You have different arrangement, different configuration, and you have different radius of gyration. You have different moment of inertia for them. You have radius of gyration. You have different moment of inertia for them. So for a sphere, for a circumference, or for a circle, moment of inertia, which is I, is mr squared all over 5. For a squared, for a circumference of a circle or a sphere, moment of inertia is equal to mr squared all over 5. That is from literature. That is not contestable, and therefore we also know that moment of inertia is also mk squared. That is how you think when you are in physics class. You have defined moment of inertia before to be mk squared. You now come to the fact that for a circumference, moment of inertia is mr squared all over 5. So if I is equal to mr squared over 5, and r is also mk squared, therefore mr squared all over 5 is equal to mk squared. Then you can now make k the center of the formula. Then you have expression for radius of gyration for a sphere to be k equals to 2 all over 5, square root of 2 all over 5 multiplied by r. So you can do that on your own to get to confirm that answer. So once you equate mr squared all over 5 equals to mk squared, then you can make k the center of the formula and see if what we have is that expression. So that is how that expression gives you the radius of gyration of a circle, and it is 2 all over 5, square root of 2 all over 5 multiplied by r. This is the difference between the moment of inertia of a body about an axis through its center of gravity. That is what you have on the page, on page 1 of what I'm sharing with you. Now, let me say, I want to share another page with you whereby we have an example. Now, you see, we cannot deal with moment of inertia without having one or two examples to demonstrate this. And of course, you can easily calculate moment of inertia, radius of gyration when you are given the known variables, and you can be able to deploy your who is raising up his hand there? Okay, you can be able to deploy the formula, put in the variable that you were given, then you'll be able to calculate whatever you have to calculate. So you have to be sure of all the formulas we are talking about here. Be sure of radius of gyration, be sure of moment of inertia, and we have discussed the moment of radius of gyration for a circumference whereby it rotates about an axis. Therefore, I have a question, I have an example there on the screen, and I want us to go through the example because this example incorporates so many other things, and you can bring them together and to get an expression for acceleration. Now, we have a wheel. Now, when you have, there are some peculiarity about symmetry, about axis, about circumference, or rectangular symmetry. But for this question, you have a question. You have description of a wheel. We say a wheel of a radius r, a moment of inertia I, is mounted on an axle supported on a fixed bearing. I will take that again, and you have it on your screen, because you have to understand the question so that you'll be able to you understand the solution. If you don't understand the question, you cannot understand the solution. A wheel of radius r and moment of inertia I is mounted on an axle supported on a fixed bearing. A light flexible string is wrapped around the rim of the wheel and carries a body of mass n. Find the acceleration of n. Find the acceleration of n. You see, you now have to put it in right perspective. M is the mass that was attached to a string that was wrapped around a wheel on a wheel. Now, that mass will undergo acceleration by virtue of that rotation of the wheel. Then, how do you calculate the acceleration of that mass? How do you get an expression for acceleration of that mass? I haven't given you that there is a moment of inertia, which is I, then there is mass, then you have to use all your knowledge of mechanics in solving this. That is why problems in physics are not done in isolation. You have to apply all the one that you have learned in the past. You have to apply it to the one you are now seeing, and you have bring out a solution from there. Now, for an acceleration, what we are trying to get is that we want to get an expression for acceleration. The first thing is that for the mass, you have two systems here. You have to be sure that you have two systems here. We have the mass that is attached to a string. That string has a tension. Then you have the wheel itself. It is the wheel that rotates that have element of moment of inertia. Now, so you have two systems that must be separated, that you have to bring together. Now, for the mass itself, the force on that mass is ma. Of course, you know that from Newton's law, that force is equal to mass multiplied by acceleration. That is correct. Force is equal to mass times acceleration. But for this mass that is on the string, now the force that is effective will be the mass multiplied by the force of gravity minus the tension. You have to understand this point very well. Because once you don't understand the resolution of this force, you will not get the solution to this problem. You have to recognize that for that mass to be attached to the string must have a tension, and the weight of that mass will also be there. It was because the weight is greater than the tension, that is why the mass could move. If the weight is less than the tension, there won't be any movement. I want to understand that, because that informs why you have mg minus t. If the tension is greater than the weight, there won't be any movement. But because we know that there is movement, that is why they have to get an expression for acceleration. Then the weight must be greater than the tension. Therefore, for the resolution of the force, it will be mg, which is the weight, minus tension. Therefore, you can now replace the force in F equal to MA with mg minus T. And that gives you the expression for equation 1, the one I named there, equation 1. That is mg minus T equals to MA. That is the tension. Is very, very important there. And before you can now resolve that equation 1, you have to remember that you are talking about will, and there's a difference between the will and the tension. That is why you have to leave equation 1 the way it is and go to the will analysis. Now, when you now talk about the will, you now see that the will, from literature, the tension multiplied by R of the will is equal to I, which is the moment of inertia, multiplied by acceleration over radius. And acceleration over radius is denoted by alpha, A all over R there. For the will, the tension multiplied by radius is equal to moment of inertia multiplied by acceleration all over R. And acceleration over R is what is denoted there as alpha. You have to circle that and take note of that. Therefore, you can now make the tension the subject of formula. Then you now have tension equals to I, A all over R squared. You replace that alpha with A all over R, then it now becomes A over R squared multiplied by moment of inertia, which is I. Now, you have gotten an expression for your T. You have gotten an expression for your T in equation 2. So, the next thing you have to do now is to put equation 2 into equation 1. You need to replace T with I, which is moment of inertia, multiplied by A R squared, all over R squared. That is what you have there. Then you put that into your T. You replace that with the T. Then you are left with mass, gravity, moment of inertia, and acceleration. Then you can now make acceleration the subject of formula. Then you have that expression for the acceleration of a body of a mass that is attached to a wheel. That is the solution. Is there any question about this problem? Because this problem entails so many things, so we have to discuss it a bit. So is there any question about this before I move on?
Yes, sir.
Yes, sir. Sir, can you please go over it again?
Yes.
Can you go back?
With access of tension and radius. Can you please go back to that asset of tension and radius equals to moment times alpha? I don't really
Okay, let me go again. You already know that force is equal to MA. And again, I also said that force, you have to resolve it because the body is attached to a string. The body is attached to a string, and in the attachment to a string, the mass also moves. Because the mass moves, we know that the weight is greater than the tension. That's the first thing, that's the technical thing in that question. You must know that the weight of that mass is greater than the tension. That is why it's able to draw, it's able to move, it's able to have acceleration. Therefore, the force will now be the weight, the effective force, or the resultant force will now be the weight minus tension. And of course, you know weight is mass multiplied by gravity. That is why you have mg there, minus T. Then you now replace the force with effective force. That was why you got equation number 1. mg minus T equals to ma. Now that deal with the aspect of the mass. And remember, we are told to find the acceleration for the mass. So easily, you can make A the subject of formula of equation 1. So, and you get an expression for your tension. But that will not be okay because the question gave you the wheel of radius r and moment of inertia I. Therefore, it means that you have to incorporate the formula from the wheel into your formula, especially in replacing tension from equation 1. And that is why I said we have to go into wheel analysis. You see, this formula you have here is like when you say force is equal to MA. For a wheel, tension multiplied by radius, that is the number between moment of inertia, radius, and acceleration. Moment of inertia, radius, and acceleration, and tension of a wheel. So it is tension multiplied by radius of that inertia multiplied by moment of inertia multiplied by alpha, and I've defined alpha for you in the circle you see there. So you have TR equal to I alpha. You have TR equal to I alpha, and you have the alpha is acceleration all over radius. So you now replace alpha wherever you see alpha with A over radius, and you get expression number equation number 2 for your tension. Once you get equation number 2 for your tension, that is tension is equal to I A all over R squared. That is equation number 2. You have gotten what tension is in a wheel. That is expression for a tension in a wheel. Expression for a tension in a wheel is moment of inertia multiplied by acceleration all over R squared. That is equation number 2. I just give you the first 3 lines so that you know you will not cram equation number 2. But you see how equation number 2 came to be. What did you say?
Please come again.
You can now see equation number 2 as tension equal to I A all over R squared. So after this, every other thing is arithmetic. Just substitute T where you see T in equation 1 and make the acceleration the subject of formula. Then you get that expression. So what other question again?
Sir, please, how did you get the formula alpha A over R?
What do you say?
How did you get the formula alpha equals to A acceleration over radius?
How do you get the formula F equal to MA?
No, alpha equals to A over R.
I'm asking you a question now. How do you get equation F force is equal to MA?
Because what is the product of the mass and the acceleration?
So that is that about that solution. So that is that about moment of inertia. Then,
Sir, please, I have a question. This acceleration equals to weight over m plus moment of inertia over r squared. Is it a fixed formula for acceleration of a mass attached to a wheel?
Yeah, that for a wheel. That's why you say for a wheel. When you are reading or when you are discussing, when you say for mass F is equal to MA. Nobody can contest that formula. That is formula. That is is another topic again for you to derive that formula. But you know that this formula is valid for any mass.
Yes, sir.
For any mass, force is equal to MA. For any wheel, T multiplied by R equals to I A R. For any wheel. So it is now left to you now to go and read about wheel to establish whether equation 2 is valid. for a wheel, tension by A all over R squared. So what other question?
Okay, that means, sir, if the weight is less than tension, that equation 1 is going to be T minus weight equals to MA.
Yes, but if
Yes,
the weight is less than the tension, there won't be acceleration.
Okay. Okay.
Oh. Esther Godwin.
Sir, I just want to ask a little question.
Godwin.
Godwin
is raising his hand. Esther Godwin.
Sir, you said that for the wheel,
Oh yeah, ask a little question. Reasonable
are
one.
we using this formula for the wheel? Sir, can you hear me?
Yes.
For this particular, like whenever we see
For the
wheels.
wheel, that's the formula you are going to use.
Oh, okay, sir. Thank you.
You see, whenever you see force, mass and acceleration.
Sir, please, sir.
Whenever you see mass and acceleration, the formula F equals to MA is always valid. So, for a wheel that is carried, that has moment of inertia, that's the difference between moment of inertia and tension over a wheel. There are so many moments of inertia that we have for spherical. You have for so many symmetry, and there is particular, just like the one we had before. This one for a circumference, you can see there's a difference between K and R. So all these formulas are valid, and they can be derived. So if you are going to derive it now, it's another thing entirely. If we are teaching you so that you will be able to write exam now, paper and pen, not multiple choice question, then we go into details of how to derive all this equation. But if I teach you how to derive this equation, how do I examine you when you are going to do multiple choice question? So that is why, instead of talking about derivation, we give you the formula, then you are able to apply it. So a good student that want to remember, you can see I'm talking. Who is the one to say sir? For a good student who now see that we have said that T equal to IA all over R squared, we now go into his textbooks and go and read more examples and be able to be proficient in this work. Don't rely on what you have, on what you do in class alone. If you do that, you will just be an average student. No, a brilliant student will go back and find out that we have said force is equal to MA. How is it so? What is force? What is mass? What is acceleration? Your lecturer says that the tension on a wheel is related to moment of inertia by equation number 2. How is it so? You go and read, and when you read, you come out with the formula, and when you are in the exam, you don't need to cram. You remember what you have read. So, what other question?
Sir, what is alpha?
Alpha is radius, is acceleration over radius. It's inside that circle.
No, I mean, what is it called?
Oh, God.
Hello? Good afternoon.
Angular acceleration.
Yeah, mo wà ní class ṣe o lè pè mí padà. Kí ló ṣẹlẹ̀? Yeah. No, sorry about that. So what was the last question? You are saying what is alpha core? When you have a symbol, that replaces that is defined for you, you define acceleration over radius. You are asking me what is alpha core?
Good afternoon, sir.
Good afternoon.
Yeah, sorry, sir. I just want to ask, in which case can we have our tension to be greater than the weight, sir?
These are type of question. Not that people will be asking me what is obvious from this slide. You see, when you see question, it depends on what you can see that this question is asking you to get an expression for acceleration. You can see the question is talking about expression for acceleration. Then because it's talking about expression for acceleration, it means that there is a movement. It means that there is a movement. If there is a movement, then our weight is greater than the tension. That is why you have mg minus t.
Okay,
now,
sir.
let's now say that the question is now calling another way, that you should get expression for the mass. I'm not saying this is the question, no. I'm just giving you an example. They now give you this type of description. They now say that get an expression for the mass at which there is equilibrium on the wheel. At which there is equilibrium on the wheel. It means that mg minus t is not valid again. Because if mg is greater than tension, there will be movement. Is that okay?
Yes. Thank you very much, sir.
It means so it depends on what you were given. It depends on the narrative or the narration of the question. Once you hear acceleration, that was why I said the only technical thing about this question is that acceleration. The fact that it moves shows that you have to get a resultant force. And the way you understand the movement will inform how you arrange your air to get the effective force. If there is a movement, it means the weight comes down, is greater than the tension, then it will be mg minus t. And that was what led us to equation number 1. Then I'm supposed to go straight to equation number 2, but I just have to pick one or two things so that you know how those things are derived. When you want to read about derivation, you can relate. So you can see that when you multiply the tension with radius, you get moment of inertia multiplied by acceleration over radius. And because we cannot be using fraction, we now replace that with alpha. So acceleration over radius could be anything. That's acceleration over distance. That's acceleration over distance in mechanics. So, any other discussion?
Thank you very much, sir. I really appreciate it. Thank you so much.
Oh, yeah, question.
Yes, sir.
Yeah.
Sir, please, I just want to be sure. The acceleration of the body and the acceleration of the wheel, are they the same?
You know the movement. Yes, because you see the wheel that moves is the same rate. It's not like okay. Another thing that will make it is the same thing. That's the answer to your question. Now, if you put a bowl of water, if you have a bowl and you put water there, and you now put a stick, you start stirring that water with a stick with acceleration of 2 meters per second squared. The way you are stirring the water in the bowl, you are stirring with 2 meters per second squared. That water that you are stirring will also be moving with 2 meters per second squared. True or false?
Yeah.
So that answers your question. Acceleration will be the same.
So I have a question.
Okay.
So I have a question.
Farida.
Okay, you said something earlier. You said to get the mass of the wheel, the mg minus t is equals to 0, because if it's at equilibrium, so it does not.
Yes.
The equation is not valid. Okay, so if we now want to get the mass, we're going to make use of F is equals to ma, and we also relate it to TR is equals to I alpha. Are those the two equations we are going to use? Okay,
you
so
see, that question was not given, no. Farida, listen.
Yes, I know.
Listen.
Because you said it.
I use that statement. Listen, no. That is why you move ahead of your lecturer. I use that statement to explain something to somebody that asked me about if is this the only way that the tension could be arranged. I now said that it depends on the way question is being asked. You respond to the way questions are asked in an exam or in any solution. This question talks about acceleration. You see, if the way what I've used as an example may not be valid, may lead to answer to be equal to 0 because it is not tested. If you say equilibrium, it means that for your force, mg minus t, we have said if you talk about equilibrium, mg minus t, it means that weight is equal to tension. If weight is equal to tension, mg minus t will be 0. And that will be 0. So you cannot, I just gave an explanation. Not a question. So you can't be asking me that way. You will see that one will lead you to 0 straight.
Thank you, sir.
That one will lead you to 0 straight.
Thank you, sir. Understood, sir.
Sir, I want to ask a question.
She's Zara.
Yes, sir. Sir,
Okay.
Can we have a situation? Can we have a question in such a way that the acceleration that is given is at an angle?
Of course, you can have that. That's why I say everything that you have been taught in physics, they are valid. Everything you have been taught in physics, they are valid. If acceleration is at an angle, or if the force is at an angle, you see, anything that is a vector quantity can be inclined. If they are inclined, then you have to resolve. If they are inclined, you have to resolve. You know that will bring you to geometry. Maybe it will be F cos theta for the horizontal, F sin theta for the vertical. It depends on the way the question is being asked. So as any vector quantity, you know, anything that can have direction, it can be inclined. Then if it is inclined, then the angle of inclination is important because you have to use it in the resolution. You know, when you are resolving vertically, you use sin theta. When you are resolving horizontally, you use cos theta. But we are not talking about inclination in moment of inertia here today, but it can be inclined.
Okay, sir.
So if you want to see more example about inclination, check your work on vectors, check your work on resolution of how to find resultant force, resultant acceleration in any configuration.
Okay, sir. Thank you, sir.
Sir.
Yes.
Sir.
Yes.
Sir, in the beginning, we said for mass m, or we all know that force is equal to mass times acceleration. So in what other scenario apart from using F minus mg minus F equals to mg minus t, where can we use mg minus t again? Apart from, like, sir, we are using the normal equation for force is mass times acceleration. That's normal definition for force. But yes, sir, why I understand, but how is it that we're not adding mg minus t in the question?
Good. These are the kind of question I expect people to ask. Not that they'll be asking me this thing. You see, like I said, the answer to your question is what I've discussed so many times here. You see, the solution, you see, in physics, there are formulas, there are models, there are numerical solutions that have been established in literature. One of such established model is the fact that for you to get force, you have force equal to LA, validated experimentally and in every sense. So when you are given a question, what you do is to use to have mass, once you know mass, you multiply it with acceleration, then you get your force. However, that force is very, very important. That your force is very, very important. Because when you talk about force, you have to look at the question you were given. Is the force they are talking about that caused that acceleration? Because you say that you are looking for acceleration of a mass, and you know that from literature, force is equal to ma. That is solid, that is confirmed from literature. But you know that there is mass, you know that there's acceleration. Then, if you now say the body is on a table and you apply a force of 20 Newton, what is the acceleration of that body? What you just do is to say the force is 20 Newton equal to ma. Then you get your acceleration straight. But this is a system. The system has a wheel. The mass is attached to a string. So the force cannot be straightforward. The force cannot be the one that you say the body, you apply a force of 20 newtons on a body. That you cannot use that, because you are now talking about two things. You are now talking about the mass being held with a string around a wheel. It means that you have two forces there. That's what I want to go. That's what I want to say. It's no longer 20 Newton that you apply to a body. You have two forces, because the mass itself will have weight, which is a force, which is mass multiplied by the force of gravity. Then the string that is holding the mass will also have tension. And tension is also a force, because without tension, it cannot hold the mass.
Sir.
So you have two forces. Once you have two forces, you cannot use F equal to ma. You have to use effective force to replace that F. If you have to use effective force to replace that F, then it means that you have to resolve the force. Then you have to think, if the weight is less than the tension, then the mass will be stationary, because the tension will have enough force to hold it at a point. But the question says you should calculate acceleration. It means that the weight is moving, the mass is moving. So if the mass is moving, it means that the weight is greater than the tension. And that is what led us to get the effective force. The effective force will be the weight minus the tension. That is what you are going to use in your head, because you have two forces in action. If you have 3 or 4 forces in action, just to say, you cannot use F like that. You have to get effective force. For that formula to be valid, that formula F equals to ma, that F is effective. If you are talking about one force, good luck, you just use F equals to ma. But once you have 2 or 3 forces, then the forces must be resolved, then the resultant force must be used. And that was what led us to equation number 1. Is that okay?
Sir, yes, sir, it's okay, sir. But sir, you said we are using 2 forces here, F equals to ma. And the second force that we're using is effective force. Sir, you said the first force we're using is F equals to mass times acceleration. Sir?
Aburume, I can't hear you.
Sir, you can't.
Aburume, I can't
sir,
hear you.
Can you hear me now? Sir, can you hear me now?
We have just 3 more minutes or 4 more minutes here.
Sir, can you hear me now?
Aburume.
Sir, I have a question.
Hello, Sele.
Sir? Sir,
Can you hear me
now?
I'm not hearing anybody again, no.
Sir,
Just
I'm
type
hearing
the
you.
question that is on network. Oh.
Can you all hear me?
We can hear
Yes.
you, sir.
We can hear you, sir.
Yes,
Sir, we
sir.
can hear you, sir.
Yes, sir. We
Can hear you,
can
sir.
hear you, sir.
Can you all hear me? I can't hear
Yes,
you
sir.
again, no.
Ah.
We can hear
Can
you.
hear
Yes,
you,
sir. We
sir.
hear you,
We
sir.
can hear
Sir, we
you,
can
sir.
We can
hear
hear
you,
you,
sir.
sir.
Maybe we should just end the class. This is
I'm
almost
checking.
time.
We
End
can
the
hear
class.
you,
We'll
sir.
continue
Sir.
next
I'm
time.
here in the class, so we sweet though.
Yes, sir.
Hello, everyone.
Hello,
We
sir.
can
We
hear
can
you,
hear
sir.
you.
Sir,
We can hear you, sir. We can hear you, sir. Loud and clear.
Hello, everyone.
Sir?
He can't
Sir,
hear
we
us.
can hear you.
Can hear you.
Sir, we can hear you.
He can't hear you say what you are saying.
We can hear you,
I
sir.
think I do that to
We
type on
can
the
hear
chat
you,
box.
sir.
Sir,
Can hear
check
you,
the
sir.
chat box. Chat box.
Femi, can you talk? I can't hear you. Farida.
Hello, sir. Can you hear me?
The man should be shut now. We can hear him.
Hello, sir.
Sir, can you hear me?
Can hear us. We can hear him, but he can't hear us.
Okay, I can hear you now.
All right.
Hello, sir.
Okay.
sir. It's my turn. Sir, it's my turn. Oh, sir, don't do. Sir, as I was saying, you said there are two forces here. F equals to
Yes.
mass acceleration, and the second force is effective force.
Yeah.
No, I didn't say this. I didn't say the second force is effective force. So I said there are two forces, weight and tension. Then you have to resolve it. You have to get the effective force. The effective force. You have to get effective force there. I'm not saying this is effective force. So that is why I say you have to now think about which one is greater than each other, and you subtract it from each other, then you get your effective force. And it's the effective force that you are going to use.
Okay, sir.
Yeah.
Sir, my question.
Okay, be fast. We have 2 minutes.
Sorry, sir. From this second equation, you said if the tension overcomes the weight, then it's not moving. Can we say that the tension is also friction in case they twist the question for us?
No. You know, when you talk about friction, friction exists between two things that are moving. Then you are not talking about tension here. You are not talking about friction here. Especially, you see, when you see a question like this, it is assumed that when you see a question like that, it is assumed that the friction is negligible. It is assumed that the friction is negligible. That is why you can see. That's why you have something like this. So, tension is not friction.
Yes, sir. Yes, sir. Understood, sir.
Another question before
Hello, sir.
Christopher.
Sir, I wanted to ask, sir, if they tell us, okay,
yeah,
the question, sir, that we need to maybe the string is in rotation.
Yes,
That
you are just setting question for yourself now. If they tell you what,
if they give us a
I
question
can't get what you are saying.
So if they say the string is in rotation, how are we going to do it, sir?
If they ask to do what?
Like the string is rotating.
It's moving.
So how are we supposed to go about it? If they say we should calculate the acceleration of the rotation.
You said those questions for yourself. I'll go and read now.
Oh.
If the thing is rotating, how will the mass move? How will the mass go to its own how will the mouse move and get its own speed or its own motion? We will answer question the way it is. You answer question the way it is. It is given to you. What is this Abudullah requesting? Remote control of your screen. What do you mean? Abud Oriola. Right? We meet on Thursday, but we have to be fast. You people have to read wide, not to use question to delay us in the class
Hello,
again.
sir. Please, can you recommend
We meet on
the physics textbook
Thursday.
for?
So
Hello, sir.
What aspect are we supposed to read
there
before the
are
class?
so many physics textbooks.
Please, can you recommend the physics for? Yes, sir.
Before
Textbook, sir. Can you recommend the physics textbook for us?
Okay.
Because I've not seen this with most of my
I will send you. I will on Thursday. I will do that. I will do that on Thursday. I will show you some of the textbooks that we are using. And there are a lot of you see.
Thank you, sir.
This aspect
God
of
bless
physics
you, sir.
that you are studying is the normal general physics. So any A-level physics, any advanced level physics, first year secondary university physics is okay. Go to the library and you pick anyone. It's okay. It's the same thing. Read all your metrics for this physics 101. It's very, very important.
Sir, please, when is our test?
Who's that? That kind of thing. Who can't ask? Who asks? Who asks?
Good afternoon. Hello, sir. Good afternoon, sir. How you doing, sir?
Nobody asked about this. I think
Good afternoon, sir.
This is gone.